the most common forms of electric power is the 50 Hertz AC power in Singapore and also in China, okay, and also in Hong Kong. But in some of the countries, it has 60 Hertz, okay. That's some fundamental things of this lecture. Now we're going to see the instantaneous power. The instantaneous power, we use the small p to denote. It is a floating element, so it is the product of instantaneous voltage and instantaneous current across this element. So the equation will be P, which is a function of time t, P equal to V times I. So this equation is the old equation for us, right? Okay, so this is the old power we have learned, but now in the AC power system, we call this type of voltage, this type of power is instantaneous power. Okay, so before today, this thing is power. So after today, this thing is instantaneous power. Okay, it is the power for a time t. Okay, for specified time t. Okay, it's not for all of the time states. It's just for one time. Okay, right. The unit of the power is watt. So it is the rate, which means the element absorbs energy in the time instant. Okay. Then in the AC circuit, we can let our Vt, because in the AC circuit, our V and I, this is our signal, right? They are our signals. Our signals should be in the form of sinusoidal signals, right? So it can be written in the form as Vm times the cosine. We know in the international things, we use the amplified times cosine something, right? But in China, we use amplified times sine something, right? Sine and previous angle t and plus the phase angle, right? Okay. So now we let our V equal to Vm, the amplitude of V times cosine over t plus the phase of voltage. Then our It should be Im times cosine over t plus theta I. This theta I is our phase of current. Okay. If we take this type of V and T and substitute those equations into the P into the I into this equation, and it will become like this. So now we know the coefficient part will become Vm times Im, right? And then we get a cosine thing times another cosine thing from this equation. Okay, this is the formula, right? This is the formula, and we can see the cosine A times cosine B should be half bracket cosine A minus B plus cosine A plus B. Remember this one, and then we compare this one with this one. If we know we can keep the Vm, Im, right, and we should times the half, then cosine it's not substitute, it's subtract, right? It's subtract, and then should be the sum. But we can see here, here we have omega t, right? Here we also have the omega t. 2 omega t become 2 omega t, right? And then the angle is the phase angle of voltage plus the phase angle of current. Okay? You should notice here is not omega t anymore. It becomes 2 omega t. Okay? From this equation, we define the first part as the constant power. Because this part, we don't have omega, the angular frequency inside. So it must be a straight line. Is it? We can see this figure is with x, t, and p, right? This thing are not decided by time t, so this one is a straight line. It's just decided by the starting phase, angle of voltage and current. But the second part, we have omega inside, so that means this one is changing with time. If the time equal to 1, 2, 3, 4 equal to something, and the value of cosine will be changed. Clearly? Okay, so this part we call sinusoidal power. And we notice the sinusoidal power, the frequency is not omega anymore. The angular frequency becomes 2 omega. Okay, right? You can see here, 2 omega, 1 omega means within a period, it's one period. It's one period. Okay, but 2 omega means within a period, 2 waves. Okay, and we can see the straight line is the first part, and the sinusoidal how to say that, curve is the second part. Okay. If the P, the instantaneous power P, is greater than 0, that means the power is absorbed by some element in the circuit. The source is releasing energy. If the power P is smaller than 0, that means the power is absorbed by the source. Okay, that means something in the circuit is releasing energy. Okay, so the question is, what type of element can release energy in a circuit? What type of element? Capacitor and
Battery.
And then anything else? Capacitor, inductance, okay? Right. And some of the how to say that, analog elements, okay?
Transistor.
Right. Yeah. Right. Now the instantaneous power, we can see it changes with time t. So it's difficult to measure this one, right? Because it's changing with time. For every time instant, it has different value. So we don't like to see it, right? So what we like to see, we have to measure something, right? But it cannot be instantaneous power. We say this thing is average power. The definition of average power is the average power big P is the average of the instantaneous power over one period. That means within the time period t, the total instantaneous power integration is the average power, and we should take the 1 over t, right? Take the integration from 0 to period t and take the average 1 over t, and then we get the average value. This definition is easy, right? Okay, this definition is easy, right? So now we know the definition of instantaneous power. That is the old definition for us, but it is changed with time now, so it's not easy to measure. So we defined another thing. This one is average power. The average power is the integration of power P and divided by a time t. Okay? Right. So if we substitute the small p into the definition of big P, and we will see the first part is a constant, right? So it is not changed. If we integrate it, it will become the same, right? So we say the second part, we also take the integration within one period and take the average. Then we will see what can we see from this part. And we know this part is the cosine function, right? And cosine function is a period, right? We know if we take the integration within a period 0 and t. We know it's a whole period, so the integration of this part will be 0. If we go back to this figure, we know the integration means the area, right? So this area and this area vanished, right? And this area and this area vanished again. So the total integration will be 0. Okay, so this thing we can observe from the figure as well. And we know you also can take this integration and you will find the same result. So we know the second part must be 0. We just have the first part. So the first part is not changed with time because we see the function doesn't have time t inside. So it's a constant, right? What type of constant? It's just a straight line. Is it? Okay, so now we are going to see the average power p. It is half Vm Im and cosine theta v minus theta I. The theta v and theta I is the phase angle of voltage and current. Are you listening?
Yeah, I'm listening.
Okay. Right. And we can see this is the definition of our P, and we calculate the value of average power. Okay. Now, because in the AC circuit, everything is sinusoidal signal, right? And we already know the sinusoidal signal is difficult to calculate. It can be calculated, but it's not easy, right? So we define the phasor, right? We learn the phasor. We know the phasor can make the calculation easy, right? It can transform an AC analysis circuit to a DC analysis circuit problem. So now we're going to see if we change the V and I into the form of phasor, what can we see? Okay, so we know the V is Vm and cosine something, right? And I is Im cosine omega t plus theta I. So from the definition of phasor, we know the V can be written in the forms of phasor. It also what type of this form called?
Ma'am, what type? This is the phasor term.
I know, but it also has another name. We have the what type of coordinate?
Oh.
So what is the type of coordinate? Is pole? Is that pole?
Polar.
Polar? Yeah, it's polar.
Polar.
It's polar coordinate. Okay? So this one is in the polar coordinate. Right. And we can see if we times V and I. Well, no, not really. If we go back to this one and we put the value of this one inside into this one, it should be angle. That should be angle. Let me have a look. Half VMIM angle theta V minus theta I. Theta V minus theta I. Right? It's nearly the same, but it doesn't have omega t inside. It doesn't have omega t inside. So can we write it like this? Yes. If we don't have omega t inside, can we write this one like this? Let me have a look. V is this one, and I is this one. So what is I star?
This is the I is the conjugate term.
Yes, I know it's conjugate, but it's same strength, because our V times this one should be this one Vm, and this one should be theta V plus theta I. Okay.
So
Okay,
theta
so
is
if we take the conjugate, it will become minus.
Yes.
Okay, if we take the conjugate, it will become minus. So this one, if we put a half here, and we keep the half here, and if we put the b here, we keep the b here, and if we put the I here, we keep the I here. But the angle, okay, here is theta b minus theta I. We know if we just times v and I, it will become half Bm Im and theta b plus theta I. But here we need minus theta I, so we need to take the conjugate of I, and it will become like this. So we know our big T in the phasor will become half V I conjugate. Okay, and then now we can see this one is actually this one. This one is in the complex form, right?
Yes.
This one is in the phasor form, and this one is in the complex form. And we can see the P is actually the real part. Where is the real part? The first part, right?
Yes.
It's really the real part of V I conjugate. Okay. But actually, we doesn't care it's real part or imaginary part. If we take the sign, it will become the imaginary part. Okay. Now we are going to see a special case. There are some special cases for the power. The first special case is when voltage and current is in phase. What does this mean? This means it has the same phase angle. If they have the phase angle, we say they are in the phase. Okay. So we should have the theta b equal to theta I. Right. If our theta b equal to theta I, and we can see this one, if they are equivalent, this part will become 0. Okay. You still remember the figure? The cosine figure is like this one, right? So when it's equal to 0, the cosine theta is 1, right? So we know now this part will become 1. So our P is equal to half Vm times Im. And if we take the Ohm's law inside, it can be transferred to a function of Im or a function of I. Right. Because our Vm is equal to Im times R. Right. Because if this part and this part is the same, actually they are a pure resistance circuit actually. Because if we have any inductance or capacitor inside, it must be a phase angle difference. Understand? So now our Ohm's law is still like this one. It just, but actually it should be like Vm equal to IV, right? But now our V is actually R plus JX, right? Now we use R is just because the X is equal to 0. Okay, clear? Right. And we say the Im square is equal to I square. I determinant square. And we know from the mathematics, our I square is actually equal to I times the I conjugate. Okay? So this one is from the mathematics definition. Right. The second special case is when the voltage and current has 90-degree difference. That means it's purely reactive circuit. Okay. If they are equal to 90 degree, and if we put this value inside, and we can see where is 90 degree, where is 90 degree, should be here, and here, right? one is the pure reactive circuit. A resistive load R absorbs power at all times. That is the fact we know. If a reactive load L and C absorbs zero average power, okay. Now we are going to see this example 1. We need to calculate instantaneous power, small p, and average power, big P, absorbed by a passive linear network. Here we give the definition of voltage and current. So, now we are going to calculate our instantaneous. Hello, do you listen to me? Okay, now we need to calculate the instantaneous power. We have P equal to VI, right? So we just put the V inside and I inside, and we get the value here, right? And we do the calculation. We know it must equal to half of the coefficient, right? It becomes 600, and then cosine the subtract and plus cosine the what? The sum, right? Cosine subtract plus cosine the sum. Easy, right? And then we get the final value. Our P, the instantaneous power, equal to something plus a cosine part. The first part is actually the average power. The second part is changing with time. Clear? So, after this, we know that this one is the instantaneous power, and the first part is the average power. This is one way. Another way is use this equation, this is formula. Our P is equal to half Vm Im cosine theta V minus theta I. This equation is the definition of our big P, right? And then we know we can transfer this one and this one into the phasor form, right? And this one will become 120 angle 45. This one become 10 angle minus 10. So it's become half 120 10 cosine the first angle minus the second angle, and we also get the same value. Okay, you can use a calculator to get the same value. This one is easy example, and now I ask you guys to try to solve the second example. And for this example, we need to calculate also the average power absorbed by an impedance V. That means now we have an impedance here. If the power V is 100 and 0 angle, just do it. Just do it, okay? Our target is try to calculate the average power, right? The average power formula is like this form. So we calculate our Vm and Im. We already have our Vm here, right? And we already have our theta V equal to 0 here. So now our job is actually to solve the Im and theta I, right? So how to get this, the Im? How to get the Im? We use the Ohm's law. Have a talk. We use the Ohm's law. I forget my pointer again. This one is easy, okay? You can use the calculator. One thing you should notice is here, this one is in the complex form, right?
Yes.
So when you finish, you will get a complex number, and you need to transfer this complex
Polar.
number to a polar coordinate. Okay? You remember the equation? A plus bj equal to a squared plus b squared. Okay? And
Equals it.
and what? Angle
Tan inverse
arc tangent
B over A.
B over A. Okay? Remember this one? A squared plus B squared, angle arc tangent B over A. Because here obviously this one is in the complex number form. And you also can transfer the denominator into the Phasor form, and then because here this one is very easy to make the deviation in the phase form, in the Phasor form. So I recommend you guys to transfer this part to Phasor firstly, then do the subtract, do deviation. Okay. You cut it here. Okay. Come on. Did you finish?
Yes.
You finish? It is better to transfer this part first. Yeah. Yes, that's first. Because, you know, if we do the deviation in the Phasor is equal to the amplitude, right? The amplitude will become coefficient, and the angle will become the angle in the denominator minus the angle in the denominator. So that will be
A series and B will keep.
yeah? Good. Okay. I think everybody get my idea. So now we are going to see the solution. So we know from the definition, but we can see from the right hand side, our Vm and theta V is here, is known. The thing we don't know is Im and theta I, right? So we need to get Im and theta I. For this one, we know we need to get the I from the Ohm's law. I equal to V over G. And our V is given by this one, 120 angle 0. In the denominator is our V, okay? And now we need to transfer the denominator into the Phasor form. And then the coefficient will be the deviation of the coefficient. And the angle will be the angle in the numerator minus the angle in the denominator. And we will get the Phasor easily. Then we substitute this one, the Im, right? And this one, the theta I, into this equation, and we will get the value. And now we will see when we put those things inside, it will become a real number, right? It will become a real number. Right, now we're going to see the example 3. We need to calculate the average power depicted, right? Supplied by the source and the average power absorbed by the resistor. So now we know we need to calculate two powers. One is average.
Average power and absorption.
Oh, it's all average. Okay. The average supplied by this one and average absorbed by this one. And now I think this circuit is already in the Phasor form, right? It's already a Phasor circuit. Okay. So we can transfer all of the things we know into the Phasor form, right? From the equation, we know the source is amplitude 5 and angle 30 degrees, okay? And then we know this one is a single loop. right?
Yeah.
A single loop, we use KVL law. Can we? Use the KVL law, we know the current inside the loop should be the voltage over the total impedance. Okay, so the total impedance should be 4 plus minus 2j.
Yeah.
Okay, then we need to transfer the denominator to the phasor, right? And then calculate the count. So what should we do next? And next we need to calculate the source, the power of the source, and the power of the resistor. Okay? So for the source, we know the P is equal to half VMIM and cosine angle voltage minus the angle current. Okay, so it should be half and 5, right? 5 is for VM, and this one is for IM, right? And cosine the angle V minus the angle current, and we get the final value. We say this one is minus. What does this mean? When P is smaller than 0,
This is power absorbed by source.
means the source is absorbing energy, right? So the energy is delivered from the inductor to the source, right? Right now we're going to see the voltage across the resistor. We see still this figure, right? We can use the Ohm's law, right? Though this is still, R is still 4, and we just times I, and we'll get our VR. So, our P, we know now it's a special case of this one, right? So, it will be half I square R, right? So, half, where is my, this one is I, this one is U. Okay, it doesn't use I square R, it is half UI. V and sorry. Wait. 哎，什么事儿？有什么事儿吗？哦，行，交多少？不是我交的。行，我跟他这样讲就好了。我现在在上课，不好意思啊。好。我晚点等我下课我就跟他打电话了。拜拜。Okay, sorry. Listen to me, okay? So, now we know our P is equal to 2.5 watts. And we can see all of the average power is used by the resistor. Is it? Because we can see here, the average power absorbed by the source is 0.5 watt, and it doesn't mean it's absorbing, it's supplying, it's supplying, because they're in the passive sign convention. This one is actually in the active sign convention, so it's supplying power. Okay, then we can see here we get the value of 2.5. That means the average power supplied by the voltage source is used by the resistor. This one, it doesn't use any average power. Clear? Okay. The capacitor absorbs zero average power, Right, now we're going to see example 4. This one it looks more complicated, right? It has two sources inside. One is voltage source, another one is current source. We need to calculate the average power supplied by each source and the average power absorbed by each passive element. Which one is passive? This one passive, this one passive, this one passive as well. Those three are passive. And this figure is also in the phase circuit, okay? It's also in the frequency domain. Now, I think they used mesh analysis for this one, because here inside we have one mesh and two mesh, right? So it is mesh analysis. Right? Okay, for mesh 1, because mesh 1 we have a current source inside. So we know our I1 must be 4 ampere, right? Our I1 must be 4 ampere. And then for mesh 2, we can write a KVL equation, right? We can write a KVL equation. So it should be this impedance times I2, right? Go right. For which direction goes to this direction. And then here, go here. It should be I2 times I2 minus I1 times 10J, right? It should be this part. And this one is voltage down, okay? But this one we put it on the left hand side, so it should be positive. Okay. Then look at this one. We can put our I1 inside, can we? Because two equations, two unknowns. One is I1, another one is I2, okay? So we must cancel our I2, and we get this value. After we get our I2, we know for the voltage source, the average power should be half, and this one is Vm, right? Half Vm, and this one should be Im. Half Vm, Im cosine, right? Angle V minus the angle I, right? Then we get the power of source 5 or element 5. So we put the P5 here. Then we get the value of P5 equal to 207.8 watts. Okay, the second one. This one is positive. That means the voltage source is absorbing. This one is absorbing energy. And the circuit is delivering average power to the voltage source. So the energy from what? Should be from this one or this one or this one, right? Okay. For the current source here, the voltage across it is let me have a look. Okay, it's analysis with this circuit, I think. So we need to take this point and this point, and we will get the value of V1. It should be, okay, let me have a look. It should be like this one. Okay, look at this one. It should be V1 equal to V2. Our V2 is 20 I1, right? And then goes here. It should be I1 minus I2 times 10J. Is it? And then we get this equation. And we also know our I1 is equal to 4, right? Put the I1 equal to 4 inside, and put the I2. We also know I2, right? Put the value of I1, I2 inside, and we'll get the V1. Okay, after we get the V1, and we know our P1, we use the equation, right? It should be minus half. Why is minus? Why is minus? Let me have a look. Positive? I1. Why is minus? Okay, because it's passive sign convention. It's passive sign convention. If it's active sign convention, it's P equal to VI, right? If it's active sign convention, it's minus VI. If it's passive sign convention, it's VI. So we know the difference if it's passive or if it's passive or active. So this one, for this V1, is obviously goes into the minus terminal, right? So it's active. For this one, it's go into the positive side. So it's passive. If we use the active sign convention, so we must put the minus here. Okay. So it's minus and the Vm here, and the 4 Im here, and cosine Vm, and go minus current base angle. Okay. And after calculation, you will get a minus power. What does this mean? If it's minus, if the power is minus, that means the power is released is no, not actually, because now it's not absorbing, it's supplying energy. Because now it's active, it's active sign convention. So now it's supplying energy. Okay, let me have a look. So when P is positive, it's absorbing energy. If P is negative, it's releasing energy. Okay. Now, still in example 4, for the resistor here, this one is resistor, right? The current goes through it is the same as the current source. So the voltage across it will be in the Ohm's law, right? V equal to IR. So if you put the I inside, it will become 80 volts, okay? And the average power absorbed is half U times I. It will become 160 watts. It's easy, right? So the only thing the only thing to make mistake is the sign of our power. Okay? So we take care about the sign of power. We notice it in the passive sign convention or the active sign convention. Okay? So the best way is just choose one. For example, if you choose the active sign convention, it's always active. If you choose the passive sign convention, it's always passive sign convention. That means we don't want your guys to use P to minus VI or something. You always use the P to VI. Okay? And then decide its release or supply energy. Okay? Don't try to use the minus VI because that is very confusing.
Yeah,
it's really confusing. Okay? So anytime just use P to VI and use your mind to decide its releasing or supply energy. Okay?
For absorbing, it will be minus.
Because you can see here, you can use the P to VI, right? And this one is in passive sign convention, right? But if they are not in the same direction, it just means you put the value of minus I inside. That's the same, you know?
Yes.
You know? So, anytime just use passive sign convention and use P to VI, okay? And put the value, change of the direction to the passive sign convention. Okay, just maybe if the I, okay, it's like this. Okay, it's like this. Okay, if this one is U, this one is I, right? And but this one is equivalent to this one minus I.
Yes.
Clear?
Clear.
And you can use the same equation, but different value. Okay, put the U inside and a minus on the side, and decide everything in the passive sign convention. Okay, I think that will be better. Now, we still have two passive elements inside. One is our capacitor. Capacitor is here, right? The current goes through will be I2 because it's in the same range, right? So our I2 is the I passing through the capacitor, and the voltage across it, we know, still satisfies the Ohm's law, right? Our VI equal to U. So we put I2 inside, and we get our V. And our P4, the average power of 4 should be half, right? Vm here, Im here, the cosine, the theta V minus the theta I, and we get this one. And we know we get minus 90 degree again. So we can see any time for capacitor or inductor, the average power is always 0. You must know this one, okay? It's always 0 for the active power, not for average power, okay? And we can similarly deliver the inductor's average power. We can see it's also 0 watts. And we must know, so this example want to show us two things. One thing is all of the average power is wasted on the resistor. The inductor and capacitor, it doesn't use any average power. Okay, it doesn't use any average power. You must know this, okay? And the power is in conservation. The source delivered energy and will be used by the resistor. Okay, delivered 100 and we use 100. It cannot be I delivered 1, you use 100, something like that. It cannot be like that. Okay. The total energy, the sigma energy should be 0. Now we're going to see the maximum average power transfer. Have you ever heard of the maximum average power?
Yes, in fourth chapter.
In the chapter 4, we learned the maximum power transfer, right? For that time, our power is all power P to VI. And now, we still have power transfer, but now, the power we have is the average power. The old power is P to VI. The average power is half VI, right? Half Vm and Im. And we can see the old P is equal to VI. Now we're discussing the average P is equal to half Vm and Im. Do you like this form? We don't like it because it's not in the same form, right?
Yes.
But no worry. It's just for this section. After this section, we will introduce the root mean square value. If we introduce the root mean square value, and this one will become P equal to V RMS times I RMS. And they will be in the same form again. Okay? So now we're going to see the maximum average power transfer. Okay, the problem of maximizing the power delivered by a power supplying resistive networks to a load RL has been discussed before. Why we need the maximum power transfer? Because sometimes, you know, in our last course, we know if we want to get the last power transfer, okay, the brush. I just review some content, okay? So this is the thing we learned. What is that? It's a Savannah circuit, right? And this one is the equivalent Savannah circuit out of the port RL. And we know if we want the maximum power transfer, we need to make RL equals RTH. Is it? But we know the R resistance is always used energy. It always uses energy. That means many of the energy is wasted on the RTH, right? So in our mind it might not good, right? But in some special cases, for example, if we use maybe for signal transformation, for signal transformation, we want the maximum power. But for the power transformation, we want the maximum energy transfer. If we want the maximum energy on this one, we have to make the RTH as small as possible, right?
Yes.
But if we want to make the maximum power transfer, we have to make their equivalent. But for those cases, the RTH, they use energy, right? The same as the RL. But why we still use this one is because for signal transformation, all of the circuit component is not big. It's small, right? So it uses energy, but it's not a big amount. It's still small. So we don't care about the energy wasted on our edge. We still want to make a big maximum power transfer because this will make our signal strong. Okay? So that is the reason we discussed about maximum power transfer. So now we'll extend this content to AC circuit. Still similar, right? We have a black box and a load, but now the only difference is, for the previous case, here is RL. Now it becomes impedance, right? Become impedance load, right? Become a VL. And here is also a linear circuit, a black box, right? But we know for any black box, we can use the Stevani transformation and transfer this one to a Stevani equivalent circuit, like this one. A Stevani voltage source in series with the Stevani impedance, right? So now we can transfer this circuit to this circuit again. This circuit is the same as this one, right? The only difference is we use the V instead of the R. We use the impedance instead of the resistance. Right. Now, we know for RTH, it has one part resistance, another part reactance, right? Resistance plus reactance J. And for ZL, we also has R and XL. Clear?
Yeah.
Okay. They are complex numbers, right? And if we use Ohm's law, because this one is just one loop, the Ohm's law is very, very easy, right? Or we also can say we use the KVL law, right? We use the KVL law should be the total voltage over the total impedance, right? The total impedance should be VTH plus VL, right? And we can substitute the value of VTH and VL inside, and we will get this form, right? So now we get our I. The average power delivered to the load will be P equal to half I square RL. Is it? Okay, now if we substitute the I inside, we will get this form. It will become the real part square plus the imaginary part square, and in the denominator is VTH, right? And times RL, because this part, half RL, right? Half RL, and those part is I square.
Yeah.
Clear?
Yeah.
Okay, because this one is I times I integrate, right? I conjugate. Right. If we know we need the maximum power transfer. That means for the real part, we need to take a derivation, a partial derivation, right? And for the imaginary part, we also can take a partial derivation, right? Partial derivation of imaginary part, partial derivation of real part, and make this derivation to be 0, right? And we get the maximum transformation. Okay, and we can see if we take this one, and this one is in this form, right? Make this form equal to 0, and we can observe what is making to 0. We know this one cannot be 0, right? Denominator cannot be 0. So the denominator should be 0 to make the total thing equal to 0. Okay? So our VTH is not 0. Clear? Because this one is the voltage, right? VTH cannot be 0. Our RL is 0? No. Our RL is not 0 as well. So we have to make those parts equal to 0. So we have XL into minus XTH. Then we take the partial derivative for RL, and we'll get this one. And we make this one equal to 0. We also know the denominator cannot be 0. So the denominator should be 0. TH cannot be 0 because it is the voltage source, right? So the thing in the bracket should be 0. And this part always positive, this part always positive, right? So if we want to make this one 0, we just make the whole part equal to 0, right? And we'll get this equation. Clear? Right. So if we want to make a maximum average transfer, then we know our XL should be equal to XTH. And our RL, look at this one, it should be equal to RTH, because our XTH is equal to minus XL, right? So this part will become 0, actually, will be, right? So put this part equal to 0 inside, our RL must be equal to RTH. So that is to say, if we want to make maximum transfer, now our RL still equal to RTH, the same as this one. The only difference is, for this circuit we don't have impedance, right? We don't have impedance part inside. We don't have reactance. So now we have reactance. For maximum transfer, the reactance relation should satisfy the XL equal to minus XTH. So we should know this thing, okay? So our ZL should be the conjugate of VTH. The only difference is here. It's not equal to VTH. It's equal to the conjugate of VTH. Okay? Right. And if you put the value of the RTH inside, and we can calculate the P max. That means if we put the thing back here, put the RTH, this one will be 0, right? This one will be 2 RTH, right? This will be the same, right? And this one will, okay, vanishing the things we want, and we'll get the final value. It will be like this one. P max will be 8 RTH over V squared. Okay, will be like this one. Right, and if the load is purely real, that means we don't have reactance, right? We don't have reactance. So now our RL will be VTH. It will become this case. Okay, clear? It will become this case. For DC circuit, the same. Okay. Right. Now we're going to see an example. What is time? 9:30. Have 5 minutes break, okay?
Yes,
I'm thirsty. maximum average power. We know the maximum power should be when the VTH equal to 0, right? So now this figure is not in the form of this one, right? So before we do the equivalent, we need to transfer the port input impedance and voltages into the Savannah form, right? So now we need to do the transformation first. Right. We know this one is our load, right? So we take the two terminals of this load and calculate the Savannah input impedance. And then we know how to calculate it. That means we set the independent source to 0. This one is the voltage source, right? Set to 0 means let the V to 0. If V to 0, it becomes short. So this circuit will become like this. And now we need to calculate VTH. It is simply series and parallel stuff, right? Then we just calculate it out. We can see 8 and minus 6J in series, so it should be 8 minus 6J, right? And then in parallel with 4 ohm, right? And then in series with 5J, so it will become like this one, right? Do you remember? Because we know the impedance for series and for parallel, the calculation is always the same as resistance, right? So we know for those two, the total one should be product of the sum, right? And then simply plus this one. Then we get a complex VTH, right? VTH. Okay, then we need to calculate the VTH. Our VTH is the open circuit voltage, right? That means we still take the terminal, right? And we need to calculate the VTH here. So look at here. We say the VTH should be the voltage on here and on here and on here, right? So now, if we are going to see this one, our VTH should be. Let me have a look. Right. VTH should be a voltage divider here. Is it current divider or voltage divider? This one is this branch over the sum, right? This one over the sum plus 10. This one should be voltage divider, right? Okay, for voltage divider, because for the KVL of this loop, we know the 10 is here, right? The voltage is on this one and on this one. So for voltage divider, we know the voltage here should be the impedance over the sum impedance times the voltage, right? The impedance over the sum impedance times 10 will be the VTH. And this one, it can be transferred into the phasor form, and we get the VTH in the phasor form as well. Then, for maximum power transfer, we know our VTH is known, right? And our VL, we know it's equal to the conjugate VTH. And VTH equal to R minus XTH. Is it? X minus XTH. And XTH, do you know XTH is here? Yes. XTH is here. And this one is the R, right? So it should be 2.933 minus J 4.467. So here we must know it's conjugate, okay? we should add a minus here, okay? And then put the value of VTH, this one inside, and put the value of RTH. RTH is this part, right? The value of RTH inside, and we get the P maximum. So this one is easy. Actually, we don't care about the XTH, okay? So the only thing we care about is RTH, right? So do we need to calculate it out? We don't care about this part, we just care about this part, right?
Yes.
Okay. Right, now we're going to see the section effective value, or called real root mean square values. In most of the time, for Chinese book, we always call effective value. Okay. Right. The idea of effective value arises from the need to measure the effectiveness of a voltage or current source in delivering power to a resistive load. The effective value of a periodic current is the DC current that delivers the same average power to a resistor as periodic current. That means, please look at this figure. This one is VT, right? We want to transfer this figure as this figure, which with effective value of voltage and effective value of current. Okay. The average power absorbed by the resistor in the AC circuit. We can use integration, right? We can use integration and take the average, and we can see if we put I square R dt inside, after integration it will become like this one, right? The average power absorbed by a resistor in the DC circuit. Notice here, this one is AC and this one is DC. It is I square R, right? Because this one is DC, right? It becomes I square R. So if we want this one and this one the same, we should let I effective equal to this one. Is it? Because you can see here, take this one out of here, right? So this one will become P, this part times R. And for the DC circuit, we should have P to I squared times R. So if we compare this one with this one, and we know our effective value of current should be equal to this equation. Clear? Right? Similarly, we can find out the effective value of voltage. The definition should be this one, the same, right? Just change the variable from I to voltage, and we get the same definition of effective value. So, the effective value is the square root of the mean or the average of the square of the periodic. This is in mathematics. Okay, this is in mathematics. It's actually the root mean square value of power. Okay, not of power, of signals. The effective value is also known as root mean square. We use the short RMS value. Okay. In some of the book we use IEFF, and some of the book we use IRMS. It's up to you. It's up to you. Okay. The RMS value of a constant is a constant itself. Okay. For a constant is a constant itself. But our signal I and our signal B for AC signal, they are not constant, right? They are sinusoidal signal. So if we take the derivation regarding to the definition of effective value, and we can get this equation, right? Just put the I equal to Im cosine omega t inside, and we fix the value because it's the amplitude. Remember, it's the amplitude. The effective value is always smaller than the amplitude. Okay, you must know this. And similarly, we can derive the V effective is the maximum of V over square root 2, and the I effective is equal to the I maximum over square root 2. So the effective value is always smaller than amplitude. Okay. And then we go back to the average power. We know the average power equation is like this one. And now it's in the form of amplitude, right? We use the Vm and Im. Now we already defined the effective value, and we can substitute the effective value instead of the Vm and Im, right? And we will see it becomes V effective, I effective cosine the phase angle difference. Then we can see now the average power absorbed by a resistor will be the coefficient, right? It will be the coefficient. The coefficient is in the same form as P equal to VI. Okay, it's in the same form equal to P equal to VI. Okay, and we use Ohm's law. We also can get I square R or V square over R. That is the same as the concept we learned in the DC circuit. That is the same. Okay, right. We should note, if we express the amplitude of a phasor in a root mean square, then all of the answers must also be in the root mean square. That just means the amplitude or the root mean square, you just can choose one, right? Most of the time, we recommend you guys to choose effective value. Okay, we recommend you guys to choose effective value. Okay, now I want to talk about something else. For the household electricity, we know the voltage in our plug is 220 voltage, right? But that is just for one phase, because we know we have three-phase motor, right? We have three-phase generator. But in our home, we just use one phase. So the phase voltage is 220. The 220 is actually the effective value. Okay, it's actually the effective value. The amplitude is actually 380. Okay, it's 380. 220 is our effective value. Okay, if you didn't remember, okay, just take your eyes to our home, because we know all of the appliance is 220 voltage, right? So that is an effective value, okay? It's not amplitude, it's an effective value. Right. Now we're going to see an example. The waveform shown is the half-wave rectified sine wave. Is it half-wave? A sine wave should be like this, right? Yeah. And we eliminated the negative half plane, right? We eliminate the negative half plane, right? We just keep the positive half plane, right? And now we need to find out the root mean square value and the amount of average power dissipated in the 10 ohm resistor. So what can we do firstly? So our job is to find the average power, right? So we know it's a pure resistor. So our P, right, must equal to V over R or I square over R. I square times R, right? So that means we need to calculate our V effective or our I effective. So for this case, it just gives us V, it doesn't give us I, right? So we must use V, right? Because if we use I, we need this Ohm's law to calculate, right? We don't need to do that, right? We can use the V directly. So now, from the figure, we can write out the equation for this figure. It's a special type of function, right? How to say that? How to say this one in mathematics? in Chinese it's 分段函数. It's section by section. It's sectional function. Yeah, it's sectional function. Okay. Right. During the 0 and pi, it's 10 sine t, right? And if it's smaller than this one, smaller than 2 pi and bigger than pi, it's equal to 0. And it's a repeat for period of 2 pi, right? It's like that. Okay, so
It's getting inside.
yeah, so this one is actually the VT, instantaneous V, right?
Yes.
So if we want to calculate the V effective, we can use the definition, right? We can use the definition. And we put the value of VT inside, and now do the integration. So now we should know the integration is for one period. This period is for 0 to big T, right? 0 to big T, but actually the big T is from 0 to 2 pi. So the integration should be 0 to 2 pi. But actually our VT is a sectional function. So we have to take this part into two sections. One is for the first equation, another one is for the second equation. Okay? Okay. So I think it might be some problem here, because here the starting point should be pi, is not 0. But never mind, because the thing to be integrated is 0. So it doesn't care about the integration limits, okay? It must be equal to 0. Right, so this part becomes 0, and we just keep this part and do this integration. And the result will be 25 volts, okay? If you calculate it out, it will be 25 volts. But here we need to use what? Integration, okay? We need to use mathematical integrations. And you also can use MATLAB if you don't want to do this integration at home. You can use MATLAB, okay? Right.
But the examination?
In the examination, you don't have mathematics.
So do like
You know, I told about MATLAB just because I know some paper guys, you're not really good at mathematics. You might don't know how to do this integration, okay? But when you are at work, when you graduate,
yes.
you don't need to know how to do this integration, right? You have computer, you have many things to help you. So it is because for me, I don't need to do this integration as well. If I see this integration in my research work, I also use computer. So why I ask you guys to do this? Okay, so you guys just know, you should know how to do this with your computer, okay? You should know how to do this with your computer. So that is, after you graduate, you still know how to do this, okay? You didn't throw it to me, okay? You don't need to throw it back, okay? Right. So we know the root mean square of V square is 25V. And take the square root and you get the V effective equal to 5V. Okay, 5 volts. And then substitute the V into the formula, and we will get our P is equal to 0.5 volts. Right. And now we are going to see the next section. The next section is the parent power and the power factor. This part is really important. And the power factor, and I know the electric machine teacher, they must mention this for many times. And they must mention the parent power and the complex power many times. But okay, I don't think it's my fault, okay? I don't think it's my fault, because this course should be on the next year of the study. But it's strange why you have this course on the 30th, okay? You know, I don't know how to say, because our bachelor is just for 4 years.
Yes.
You have 2 years study here, 1 year for the degrees, and another year to find your job, and then you graduate. You know, I feel it will be a problem, because you don't learn enough things from the university, you know. So after the university, I recommend you guys, when you go back home, I recommend you guys to see as more online course as possible, to see online course as more as possible, because if you don't learn anything from the university, that means when you graduate, you have to learn this at work. It will be a problem.
Yes.
You still have to self-study, okay? So anyway, when you are still at home at school, try your best. Okay, try your best. Okay.
Yes.
Right. Now we're going to see apparent power and power factor. Apparent power, we know from the definition of the average power. Now, when we introduce the real mean squared value, and we can transfer the p is equal to a function of v effective and I effective and cosine the phase angle difference, right? And now we define the v effective times I effective as the apparent power. And the angle, the cosine of the angle difference, phase angle difference as the power factor. And we use the short PF. Okay, we use the short PF. Our apparent power, we use the S, the big S to denote it. The big S is the product of the root mean square values of voltage and current. It's easy to remember, okay? So before, we know P equals to VI, right? Now we just change to S equals to VI. Easy? That is like in the DC we have R, right? In the AC we have V. It's more like this, okay? Right? The S, the apparent power, is also measured in watts times ampere, or you also can write down AVA to distinguish it from the average or real power. For power, we use what? The unit power.
What?
But the unit of apparent power
VA.
is VA. Okay, so it's different.
Yes.
When you sometimes you say the label of a device, of appliance, you can see something to denote the total power, or it should be like maybe the unit should be in watts or in VA. But if it's in VA, you must know it's total the apparent power, okay? If it's in watts, it's the real power, okay?
Yes.
Right, now we're going to see the power factor. The power factor in short of PF is the cosine of the difference between the voltage and current. It is also the cosine of angle of the load impedance. We should know this of the load impedance. Okay, so that means the voltage on the load minus the current on the load. They have different phase angle, right? So the different phase angle is the value of C to V minus C to I. And the V and I is the voltage and the current goes through or on the load. For this we should know, okay? Now, the power factor angle is also called phase difference angle. It's also called phase difference angle. Or also called the angle of load impedance. Angle of the load impedance. And we know for our impedance, we have Z equal to V over I. This is for the Ohm's law, right? And if we rewrite this one and this one into the phasor form, we will have Vm angle theta V over Im angle theta I, right? And we can write it into the phasor form, into the polar form like this. And we can see, because our Vm is equal to R effective times root square of 2. And our Im is also equal to I effective times root square of 2. And we can see in the denominator and in the numerator, we have square root 2. We both have square root of 2. So they will be eliminated. So our V, if we take the effective value or we take the amplitude, the result is the same because the coefficient is eliminated. Okay? Now we're going to see some content about the impedance triangle. We have many triangles in our electrical definitions, and here is the impedance triangle because we have our Z equal to R plus Ix. The R is the resistance, the X is our reactance, right? And the angle is, the Z is this one and also this one, right? And our R is this one and our X is this one. The only difference is we know for an inductor the impedance is always positive. For a capacitor the impedance is always negative. Clear?
Clear.
So if it's positive, it's pointed to the positive direction. If it's negative, it's pointed to the negative direction. So we can see the angle difference direction is not the same. They are opposite. Okay? So if it's inductive, it's positive. If it's capacitive, it is negative. Clear? Right. And if we write it in the form of the VI relationship, it will be like this form. We know for a capacitive, the voltage. Let's have a look. For inductive, the voltage is always leading the current. For capacitive, the current is always leading voltage. Why? I want to ask you guys why. How to decide which one is leading the other. The reason is that please look at those two equations. This one is for L, this one is for C. This one for inductance, this one for capacitance. And we know our D cannot change instantaneously. Our V cannot change instantaneously as well. So if we give some excitation on this one, for example, this one is a inductance, right? If we give some voltage on it, or if I give some current into it, we know the current cannot change instantaneously, but the voltage can, right? That means, okay, for example, in the beginning, our voltage and current is the same. For example, if it's 0, okay, no voltage and no current, right? So it must be in the same direction with the same phase angle, right? Okay, so if I give some excitation, right, the value will be changed, right? But we told you guys all the time instance 0 plus, I cannot be changed. Why? We know if we draw a figure, right? If we draw a figure, we know if we change a time t, that means the dt is tends to 0, right? If it changes instantaneously. This one may be a constant, maybe I give it a constant 10. It will be very, very large, and the big voltage will be very, very large when it will make a big problem, okay? It will be fired. So we say I cannot change instantaneously. So I still here. We say after time t, after we add this excitation, the I still here, but the V goes away. So for inductance, the U is leading. U leading. So you can see here, this one, right? V is leading, right? Okay, go back to capacitor, okay? Okay, now we say for capacitor, if we don't give it any energy, in the beginning, it must be like this one. Zero current and zero voltage, right? And if I add excitation on this capacitor, okay, we know the signal will change. But look at here. We say the V cannot change instantaneously because when ET tends to 0, if the dV changes instantaneously, it must be equal to some constant, right? If the constant is 10, we know for a max equation like 0 and 10, it will become a very, very, very large value. And this very, very large value will make this current very large. It will fire this element, right? So after we add this one, we know the V cannot change, the V is still here, but the I goes away. Clear? So actually we don't need to remember this one, but we need to remember this equation, right? And after simply analysis, we must know which one is before, right? Clear? Right. Right, I hope you guys can understand things in your mind, not just to remember it by heart, okay? Right. Yes, if we remember it by our brain, sometimes maybe after 3 years, we forget. But if we remember the equation, we know the reason. We just take a short time to derive it and we get the result, okay? Right. Now, we are going to see this table. The table shows the apparent power and power factors. This one is impedance, V, and this one is the VI relationship, and this one is the power relationship. Right. Here shows the type of impedance. If it's a pure resistive load, that means we just have resistance inside. We don't have inductor and capacitor, right? And we know now they are in phase. They are in phase. So the phase angle difference is 0. Our power factor is 0, is 1. So we say this one is the ideal state. Why? We say this one is ideal state because we know it's all real power, right? In our power grid, the energy we use is actually the real power. The active power is actually just transfer. Okay? We don't use it, we just transfer. So we say if the power factor is 1, it's the ideal state. And in our real practice, we want to make this power factor as large as possible. But is it possible? No, because our load is inductance, right? Our load is inductance. For example, inside our inside our appliances, machine, devices, the components inside we have resistance, but we also has many of the coil inside. We have many of the coil inside. The inductance make the circuit inductive. So we say for big power grid, the power factor is not possible to be 1, but we want to make it large as possible. Okay, that is our objective. We should know this. Okay, right. The power relation for P and S is equal to 1 because now we don't have any active power component. We just have real power component inside. All powers is consumed by resistance element. The second one is purely reactive load. For this state, we don't have any resistance, right? That means the power is not consumed. The real power is not consumed. We just use active power. But we know active power is not used actually because the integration is zero. Sometimes it's releasing and sometimes it's saving, releasing, saving, releasing, saving, something like that. So the integration is always zero. For this one, the power factor is zero. It's easy to remember, okay? The power factor is zero because the power factor is cosine theta, okay? It's cosine theta. So do you still remember the figure I draw for cosine? Okay, sometimes if you are not clear, just draw sine figure, cosine figure, tangent figure, something like that. Remember this figure in your heart, okay? Remember this figure in your heart. So for this case, our real power P is equal to 0. No real power is consumed. The third case is resistive and real reactive load. This is the most common case, right? That means in a circuit, we have resistive load and we have reactive load as well. And now, if our theta B minus theta I is greater than 0, what does this mean? Means V is leading, right? V is leading means inductive load.
Yes.
If the theta B minus theta I is smaller than 0,
Right.
see this case? So it must be capacitive load, okay? So sometimes we don't care about is it intuitively, inductive or capacitive, okay? But we need to know how to judge, okay? Now we're going to see the example. The example 1 is a series connected load draws the current. The current is given by this equation, and we apply the voltage on it. The voltage is in this form. They are in the same angular frequency, but different phase angle, right? Different phase angle. We need to find the apparent power P and the power factor of the load. And we also need to determine the element values that forms the series connected load. Okay, now we're going to see the first problem. We need to calculate our apparent power. We know it's equal to the V effective times the I effective, right? Our V effective here, right? This one is not effective, it's amplitude. So the value of this one is 4 over 1.414, is it? So 4 over 1.414, and for voltage is also equal to amplitude over 1.414. Okay, then after calculation, we know square root 2 times square root 2 becomes 2. So we easily get the result is 240 VA. Remember the unit of the apparent power. Okay, it's U in watts. Now we're going to calculate the power factor. The power factor is equal to the cosine. Okay, take the cosine of the theta V minus theta I. Okay, theta V minus theta I. So our PF which is equal to cosine minus 30 degree. Okay, take the calculation, and we know the power factor is bigger than 0. If it's bigger than 0, go back to this figure, we say it's inductive load, right? It's inductive load. The voltage is leading. The voltage is leading. Right. Now, when we calculate the S and V, we're going to calculate the impedance, right? The total impedance is equal to the voltage over the sum. We know here, for impedance, we know if you use effective value, it's okay. If you use amplitude, it's okay as well, because it doesn't affect the result. Okay, it doesn't affect the result. So we just put 120 and 4 inside, right? And put the angle inside, and for phasor, we just equal to the angle in the numerator minus the angle in the denominator, and we get the result. It's easy, right? And if you can transfer this one into a complex form, like this one, use the equation I put before, a plus b, right? a plus bj equal to a squared plus b squared and square root, and angle arctangent b over a, right? Right. So we know now the load impedance is a 2590.98 ohm resistor in series with the capacitor, which is 15, right? And this minus means it's a capacitor, right? It's a capacitor. And this capacitor is equal to 1 over omega c. So our omega, from this equation, we know our omega is 100 pi, right? The frequency angle, we can take it from the definition of IT and VT directly, and substitute this inside, and we can get this C. Clear? Okay. Now we're going to see the example 2. Now we need to determine the power factor of the entire circuit and calculate the average power delivered by the source. Now we want to calculate the average power P, right? Okay, now we can see this one is in the frequency domain already, and all of the impedance are in a single connection. So we can calculate the total impedance, right? To calculate total impedance, we know those two are in parallel. So the sum over the product of the sum, right? Product of the sum and plus the 6, and we get the impedance is 6.8 minus j, 1.6. And if we change this complex form into the polar coordinates, into the phasor form, we will get our z into this one. So now we can see our power factor should be cosine. Cosine what? Cosine, maybe one angle minus another angle. But here we can see this one is actually the impedance phase angle. Okay, the impedance phase angle is actually this value. So when we take this value, we can just put this value inside, and we get the vector power. So there are two ways to calculate the power factor. One way is calculate the V and I phase angle and take the subtract. Another one is calculate the phase angle of the load and just put the value inside directly. There are two ways to get the power. Now, we're going to calculate the current supplied by a voltage source. But we know now we need this Ohm's law to calculate the I, because because we are going to calculate the average power supplied by the source, right? The average power is equal to V, I, and power factor. So our V, do we know? V and I we can calculate, right? We can calculate the V and I. We already know the V. Do we know the V? Do we know the V? Can we have a look? It does V is here.
Hi, zero.
V is here. B is here, but we don't know the I, right? We don't know the I. But we can calculate the I, right? Because we already know this one is a simple circuit, right? We can put it into the formula like Savannah circuit, right? And it will become just one loop, and we can calculate the I here. And then we know, if we know the V here, right? But this value is not root mean square. We take this one over square root 2, okay? And we need to put the root I effective inside. The I effective is also not this one. It should be this one over root mean square of 2. Okay? Not over root mean square. Root square of 2. And power factor, we already know is nearly 1, right? Nearly 1. Put all the value inside, and we get the power, the average power P. So, now we see today's course, we just told you guys the definition of something, right? And give you the formula of this definition. And if they ask you guys to calculate one thing, just write down the formulation and then try to find out the variable in this formula. And then you will get the result. It's really easy, right? But there are something we notice is sometimes we use the Savannah equivalent, right? When we use Savannah equivalent, we need to do some circuit transformation. We need to do some circuit simplification. That is the skill we learned from the DC part, okay? Right. And then we also can use another equation, P to I effective square times R, okay? Okay, so now you have one point in your mind. The equation or the formula about our P is always the same if we take the effective value. Clear? If we take the effective value, the formula is always the same as DC circuit.
Yes.
Okay? Okay, now we're going to talk about the complex power. Another type of power again. For complex power, complex power is usually when finding the total effects of parallel laws. It contains all the information pertaining to the power absorbed by a given law. The complex power S is the product of the voltage and the complex conjugate of the current. So, this one gives us the definition of complex power. So we know the apparent power S, right? Apparent power S is equal to U or VI, right? But this U and I is effective value. But for the complex power, it's equal to VI conjugate. The only difference is here, the conjugate. That means the imaginary part is taking the negative. Okay, taking the negative. Right. Okay. We know if we take the phasor form of voltage and current, it will be in the form like V equal to Vm square C to V, I equal to Im C to V.
Yeah.
The complex power is defined as this one equal to half V times I conjugate. If we use the root mean square, it will become V root mean square or V effective times the I effective conjugate. Okay? And this one, if we write this one in the phasor form, it will become V effective, I effective, and angle C for V minus C for I. It will become like this one. So, is it similar like the P? Do you think it's similar like the equation of P?
No.
Why not?
Here that's not how.
Why not? It's similar, right? It's similar. When you go back, you remember this one, okay? You remember this one, and when we go back to the P definition,
Then how to school there? Understand that.
you will see where is P. Clear?
Clear.
Clear?
I think maybe there is
But here is not cosine. For complex is angle, right? For complex is angle. It's similar but not the same, okay? Okay, so it's like this one. And for this one, we can expand it, this one into the complex form. It will become like this one, right? It will become like this one if we take the this one like cosine theta plus j sine theta.
Yeah.
It's like the ej theta equal to cosine theta minus plus j sine theta. It's a Euler equation. Euler equation, okay? From the Euler equation, we can transfer this one to this one. And the first part we call is P. Because this one is really the same as the value of the average power, right? The same as the average power. This part we call its real power as well. So the average power is also the real power. It's the same thing, but different name, okay? Right, the second part, okay, except the imaginary g, the left things we call the active power. We use the Q to denote it, okay? So the difference is the left side for P is cosine, for Q is sine, okay? Right, P we have learned, but Q is the first time we see it, okay? Right, the Q is called the reactive power. It is a measure of the exchange between the source and the reactive part of the load. That means the Q is not wasted, okay? It's just the energy transfer from one to another, or another time from this one back again, okay? It's just energy transfer. Right, and we use the VAR to measure the reactive power. So for apparent power, we use VA to measure it. For P, for real power, we use watt to measure it. And for reactive power, we use VAR to measure it. Okay, we know difference. It's measured in volts ampere reactive. So we use VAR to measure it. Because it's different, right? It's similar, it's in the same equation, but the mean is different. So we use different units. Okay? If the Q equals to 0, it means there is no reactive things in the circuit. It's a pure resistive load. Okay? So we have unity PF equal to 0. If the Q is smaller than 0, it means it's compact load. We have a leading PF greater than 0. If Q is smaller than 0, it's obvious because we know everything related to capacitor is negative, okay? Imaginary and a negative thing means capacitive, okay? If the Q is greater than 0, this part is bigger than 0. That means it's inductive things, right? Inductive loads, it has a lagging power factor less than 0. Okay? It's easy, right? The definition is easy. When we know the difference, we know the definition is easy. But sometimes still confusing. But we should know the difference. Right. The complex power can be expressed by the load impedance. For example, here is a circuit. This is actually a port, right? It's actually a port. Here is the load, and we know the voltage on the load is V, and then the current passing the load is I. And we know the impedance is consisting of resistance and reactive, right? So it can be written like V equal to R plus JX. And we also know it can be written in the form like this. It can be V effective over I effective and angle theta V minus theta theta v minus theta f. So this one, it also can be Vm, right? V magnitude and I magnitude. It's the same, okay? Because we know for the Ohm's law, we know for the law it satisfies the Ohm's law as well. We have V effective equal to V I effective. So our complex power S is equal to V effective times I effective conjugate. And we can take this one in terms of the I effective and V. So if you take the S as the P, it will become P equal to I square R, right? So it's actually the same equation as the DC. If we take the S equal to I square P, okay, it's actually the same, okay? If you didn't remember, don't worry. Recall the formula of DC, right? And change the variable. You get the formula of AC string. Right? So there are two forms. One is in terms of I, another is in terms of the V effect. Okay? Right. If we take the complex power in terms of the I effective, and we can substitute the impedance inside, we will give this one. And we break this bracket, and we will see the first part is I square R, the second part is J I square X. And this part we know is actually the big P, right? The second part is actually the Q. Okay, so now we should know the real power P is equal to I square R, the same as the Q resistance, right?
Yeah.
The second part Q is equal to I square X. Okay, so it's actually the same. Now we're going to see the complex power. Introducing complex power enables us to obtain the real and reactive powers directed from voltage and current basis. That means in our circuit, we have real power and we also have reactive power. But sometimes we need to discuss them separately. But if we introduce the complex power, we can calculate them directly. Just because for a complex number S, the real part is our real power. The imaginary part is our reactive power. So that means the complex number is a mathematical skill we use to make calculation easy. Okay, you know this. We don't have real. It actually, in the practice, we don't have a real complex power. We just have P and Q. But complex power is a mathematical skill we introduced to make our calculation easy. Clear? Okay. Right. Now, we say, if we substitute our P and Q inside, and we'll get our S is equal to V effective, I effective, cosine theta V minus theta I, plus J, V effective, I effective, sine theta V minus theta I. Is actually, we can change this one to theta L, right? Or theta V. This one can be changed to theta L, this one can be to theta L as well. This part can be transferred to power factor as well, right? Remember? Okay. Right. And this one is another form of S. Okay. So in our calculation, which one do you prefer to use? It's up to the condition it gives us, right? If it gives us theta V, theta I, V effective and I effective, we can use this one, right?
Yes.
And we also can use this one. That's the same. It's up to me and up to you. It's up to you guys. It's regarding to which form do you want. If you want complex form, we use this one. If you want the phasor form, we use this one, right? now we're going to see this one. It looks like a conclusion. Okay, it looks like a formula conclusion, right? We know complex power S is defined like V effective I effective angle theta V minus theta I. The apparent power is different as the complex power. This one is a big S with how to say uniform. It's uniform. 加粗 make it strong. You can see you compare this one with this one. This one is strong one. This one is slim one. Understand?
Slim.
No, not slim. I know. I mean, okay. When you use a word, okay, if you want to emphasize something, you will make it large. So this one is I don't know how to say this function.
Polar? No. Polar?
Polar? No, I don't think that. I mean, for this character. For this character. Okay. We have the slim S, okay? And we also have the fat S.
Mod.
Borderless.
Mod. Absolute value.
M-O-L-D.
Mod. M-O-D.
M-O-D.
Absolute value, that means.
I don't know. Okay, anyway, I have my mobile.
That is means absolute value.
I just check what I want to say, okay?
Okay.
Bold. Yes, it's bold. It's bold, not bold. It's bold, I remember.
I'm bold and more this is absolute value.
I know, but I don't know what is mold, but I know bold, okay? Bold is just make this letter text. Okay, anyway, ignore it, okay? My English is not that well. You know, sometimes if you not always use English, sometimes you will forget something. I know you guys, you know a little bit Chinese, okay? But when you go back home, you didn't use Chinese, you must forget it. Okay? You can say hello, my name is what. I work in something, and other things you forget, okay? But then I know you definitely should know how to say the fruit name, okay? The fruit name. You know how to say that in Chinese, I think. Okay, right. So we use the bold letter to instead for complex power, and we use the slim S for the apparent power. Okay. So the slim S is the determinant.
Absolute.
It's just determinant. Okay. If we don't say determinant, do we have another word? Determinant.
Determinant.
No.
Absolute.
Determinant. Okay, anyway. Right. And it's equal to the V effective times I effective. That means you ignore the angle, and the left things is apparent power. Okay? And the value should be the P square times Q square, and take the square root. Okay, for the real power, is the real part of the complex power is equal to the apparent power S times cosine theta V minus theta I. Is also equal to S PF, right? S times power factor. Okay. For reactive power is equal to the imaginary part of the complex power is equal to S sine theta V minus theta I. Okay. The theta V minus theta I, we also can use the theta L instead of it. Okay. For power factor, PF is equal to the remember, it's the real power of the complex over the apparent power. Real over the complex of the apparent. Okay, so it's equal to the cosine theta V minus theta I. Right now, we are going to talk about is the triangle things. Our S, okay, this one is our complex complex power, right? Our complex power is equal to P plus Qj, right? The P is the great part. The Q is the against part. Okay. And we can draw two triangles here as well. So before that we have impedance triangle, right? Now we have the power triangle as well. For power triangle, we have the S, right? The S is here, and the P and the Q, right? And the theta is the angle between the S and the P. Okay, because this one is power factor, right? So it cannot be this one. Because it's the relation between P and S, not the relation between Q and S. It's easy to remember, right? Right. So for impedance triangle, we also have we have introduced, right? So this one and this one, they are similar. Do you notice that? They are similar. So we know the power, the real power is related to resistance part.
Yes.
The Q, the reactive power is related to the reactance part. Okay, so the apparent power, the complex power is related to the total impedance part. Okay, and then here we show the lagging things and the bleeding things. And for this one, I think we don't need to introduce it again. Because for the positive thing pointed up, for the negative thing pointed down, right? And we know the difference of leading V. This one V is leading, this one I is leading, right? So which one is conductive? Which one is inductive? Capacitive? Inductive? Which one? Remember? Compare this one. For C, I is leading, right? For C, I is leading. So for C is like this one. Okay, clear? Okay, when you go back home, just practice how to see which one is leading, which one is capacitive, just using these ones. Okay, you need to practice and make it more and more familiar. Okay. Right now we are going to see example 1. Now, please look at this figure. We give V and I for this part. We need to find out the complex power and the apparent power. Complex power means big S, right? Bold S. Apparent power means slim S, right? And the real power means P. The reactive power means Q. And PM, and the load impedance V. We need to calculate out many things, right? Okay, so it already gives us the V and I in the sinusoidals. So the first thing we need to transfer this one into the phasor for calculation, right? For phasor, we know omega, we ignored it, right? And then for this one is amplitude. We need to transfer this into effective things, right? So it should be 60 over 1.414 and angle minus 10. For this one the same. Transfer this to effective things, right? Put this magnitude over 1.414 and times the space angle. Then the first one we need to calculate the complex power. We know it should be the V effective times the I
effective
conjugate effective, right? So our S should be 45 angle minus 60 degree VA. Okay, remember the unit. When you go back home, you have a try, okay? And if we transfer this one into the complex form, it will become a real particle than imaginary, right? And here we know the apparent power is the determinant of it, right? It's here. When you take the determinant, just take a squared plus b squared and take the square root, and you also get the same value. And we can see the unit of the apparent power and the complex power is the same. Okay, is the same. Right. The second one, we need to calculate the real power. We know the real power, just take the real part of this one. So it should be this one. The reactive power, the imaginary part, don't forget the negative So the value is 0.5. It's very easy, right? Just use the formula we learned in today's course and put the value, the known value inside, calculate the unknowns. Really easy. For load impedance, our Z is equal to V over I, right? You can take the amplitude things and you also can take the effective value as well. And this one will be 40 at the end load, right? So, okay. So then this example is finished. Now I ask you guys to solve this example. Okay, have a try. Have a try. This one we need to calculate the load. This load draws 12 kVA at a power factor of 0.856. Lagging. Lagging means minus, right? Minus 5. Minus.
What is this?
Let's have a look. Why is it talking about lagging? Right, so it's lagging from 120. The inductive sinusoid source. Lagging. Why is it lagging? Lagging is minus, right? Leading is positive.
No. Page 65. The right lagging is positive. I have also put it.
Lagging? Positive?
Page 65. Yeah.
Lagging? Okay, lagging is positive. Sorry.
No. I am confused. Some of book writing lagging is negative. Some of book writing lagging is positive.
No possible. There's no possible.
Okay, I show you. I will show you.
Lagging means something lagging with something. Right?
Is it negative or positive?
Lagging means lagging. I think it's regarding to the target. It is talking about the current. It's about your voltage regarding to the current or current regarding to the voltage. I think it's different. If you talk about the voltage, if the voltage is V, that means sigma V minus sigma I. This must be positive. Right? Must be positive. Sigma V positive means it's inductive. Right? It's inductive. So I don't know why to say lagging. Lagging.
I think this one will be leading, right? Leading up, letting down.
The V is leading. V is leading means the lagging here means the cosine. I think that's why the cosine stuff is like this, right? If the cosine is positive here, negative here, it's all It doesn't matter.
Normal book and they say lagging 0.8 meaning minus cos inverse 0.8 equals to tau, cos inverse 0.8 equals to
I think it's not a problem because this one just a name. So the actually if here is the p is greater than 0 or is minus than 0, but actually it says when it's lagging and this one is greater than 0, it's up here. It's up when it's up here. When it's up here, it's theta v minus theta I bigger than 0. When it's smaller than 0, it's still positive actually. So I think the problem we want to solve is p is always positive. Is that p is always positive? P is always positive.
P is always positive.
Positive is always positive, right? But lagging and leading is for what? That's the main issue. What is leading and lagging for?
Like, remember, if any example, if they say lagging 0.8, so if I need to find the theta, so theta equal minus cos inverse 0.8 or
I think leading means
positive.
something leading something. Current leading voltage. Lagging means current lagging voltage. So if you change your habit,
Like voltage,
like voltage,
current.
that's so I don't think it's a problem with this event. This event. So the fact is still there. Okay.
I believe that, but my question is, if I use leading, should I have to use minus or plus? If they say lagging,
Plus.
for lagging is plus,
Because you say the P is always positive. So we cannot be very positive.
but one is
But, okay, sometimes the P can be
Negative.
So it's not always positive. I can then go back to see the definition, and you also can see the definition, so we get what is the P. If it's lagging, it must mean something lagging for something. Leading must be something leading for something.
I'm curious here, like,
And here I see, if the angle is maybe using 90 degrees, it's always positive. You know. For example, if okay, for example, in this case, if theta v minus theta I equal to minus 90 degrees, it's still positive. Understand? So that will be a problem. I think the problem is in Chinese, the phase angle is from minus 100 to 100. But for international, it's from 0 to 6, 360 degrees. So I think that is the problem. So it can just can go this way, not go You want to calm? And you become more insane, but it's still positive.
Yes.
Still positive, so it's still thin. Still thin. It's still thin.
It means theta b minus theta I equals I b minus 30 degree. So this is it.
Yes, and then it's here as well.
Here you go.
So, okay, so I suppose theta b equal to 70, okay? Theta I equal to 80, okay? So, our theta b can be changed to the same, right? The same. Still the same.
Basta. Nag-ubaya ko na lang. Then, ako yung nalalang sila yung walang model.
So how did you do that?
강화를 왜 강화를 받죠? 이거 그냥 뭔가 qua tuần có được 3 bảy